All right, welcome. Today, we're jumping right in to decode the language of water. If you're studying or just need a solid refresher, this is your ultimate revision guide to the essential parameters that define water quality. So, why do we bother with all these tests in the first place? Well, it really boils down to these three critical reasons. This isn't just about passing an exam. It's about keeping people and our environment safe and making sure the complex machinery of our treatment plants is running exactly as it should. Think of these parameters as the vital signs of our water. Here's our game plan. We'll start with the physical stuff, then get into the big one, oxygen demand. After that, we'll tackle nutrients, the water's chemical balance, hardness, and wrap up with some key contaminants. Let's get started. First up, physical and aggregate properties. You can think of these as the initial checkup for a water sample, the things we can see, feel, and weigh before we dive deep into the more complex chemistry. We're going to start with total solids, or TS. The concept is super simple. You take a water sample, you gently evaporate all the water away, and you weigh what's left behind. That residue gives you the total load of everything in the water that isn't, water itself. Now, we can split those total solids into two categories using a simple filter. Everything that gets caught by the filter, that's your total suspended solids, or TSS. This is the gunk, the particulate matter that makes water look cloudy. Everything that passes through the filter is your total dissolved solids, or TDS, things like salts and minerals that you can't see but can definitely affect the taste. Okay, so how much of that solid material is organic? To find out, we take that dried residue and we bake it. Really bake it, at 550 degrees Celsius. The portion that burns off is what we call volatile solids. This is a super important number because it gives us a rough idea of how much organic food is available for the microbes in our biological treatment systems. Now, here's a key distinction. Turbidity is not the same thing as suspended solids. We're not measuring the weight of the particles here, we're measuring the water's optical clarity. We literally shoot a beam of light through it and see how much that light scatters. This is absolutely critical for drinking water because tiny particles can act like little shields, protecting dangerous pathogens from our disinfectants. And finally, in this section, we have color. We have to be specific here because there's apparent color, what you see when you look at raw water, and then there's true color. True color is what you measure after you've filtered out all the turbidity. That leftover tint tells you about dissolved stuff, anything from natural tannins from leaves to nasty industrial pollutants. Okay, so we've covered the physicals. Now, let's get to the heart of the matter for wastewater, organic pollution. This next section is all about how we measure the impact of that pollution, specifically, how it sucks the life-giving oxygen right out of a body of water. Let's introduce the two heavyweights of oxygen demand, BOD and COD. BOD, or biochemical oxygen demand, is the natural approach. It measures how much oxygen tiny microorganisms will use up as they eat the biodegradable waste. COD, on the other hand, is the fast and furious chemical approach. It uses a powerful oxidant to measure the oxygen needed to destroy nearly all the organic stuff, whether it's biodegradable or not. BOD is what we call a bioassay, which is pretty cool. We're using living things to tell us what's going on. The equation looks simple. You take the initial dissolved oxygen, D1, subtract the final dissolved oxygen, D2, and divide by P, which is just the fraction of your sample. This result directly simulates what happens when waste hits a river. Now, the BOD process isn't a straight line. It starts off fast and then slows down as the organic food gets eaten up. This first-order reaction equation here just describes that curve. It lets us predict the BOD at any time t based on L, the ultimate or total BOD, and K, the speed of the reaction. So this is the classic 5-day BOD test procedure. We take our sample, dilute it with special water that has nutrients and some seed microorganisms to get things going. We measure the oxygen, seal the bottle up tight, and then stick it in an incubator for 5 days. And this part is crucial. We keep it in the dark. Why? To prevent any algae from growing and producing their own oxygen, which would totally mess up our results. After 5 days, we measure the final oxygen and plug it into our formula. Now let's talk about COD, the inpatient cousin of BOD. Who has 5 days to wait for an answer, right? With COD, we use a really strong chemical, potassium dichromate, to just blast apart and oxidize all the organic matter. The big advantages here are speed, you get your results in just a couple of hours, and the fact that it measures non-biodegradable organics that the BOD test would miss. So if you look at a sample of typical wastewater, you'll almost always see that the COD value is higher than the BOD value. And that makes perfect sense, because COD is measuring pretty much everything, while BOD only gets the fraction that bacteria can eat. That gap between the two bars is really useful. It tells us how much of the pollution is resistant to biological treatment. A big gap means a tougher waste to treat. All right, organic pollution isn't our only headache. Wastewater is also loaded with nutrients, mainly nitrogen and phosphorus. Now, these are essential for life, but in wastewater we have way too much of a good thing. This excess leads to a nasty problem called eutrophication, which is when you get those huge, choking algal blooms in our lakes and rivers. Nitrogen is like a chameleon. It's always changing its form in the water. It starts out as organic nitrogen, locked up in proteins and other compounds. As things decompose, it gets released as ammonia. From there, special bacteria convert that ammonia first into toxic nitrite and then finally into nitrate. Understanding this cycle is the key to removing nitrogen. Now, measuring each one of those nitrogen forms separately can be a real pain. So, we often use a handy shortcut, the total Kjeldahl nitrogen test, or TKN. This test is designed to measure both the organic nitrogen and the ammonia nitrogen together in one go. It gives us a great snapshot of the total reduced nitrogen we have to deal with. So, you might be asking, if we can just measure TKN, why do we even care about all those different forms? Why not just measure total nitrogen and be done with it? Well, it's a great question, and the answer is that each form has a dramatically different impact on both the environment and our health. And here's exactly why it matters. Ammonia is directly toxic to fish, plus its conversion to nitrate consumes huge amounts of dissolved oxygen. Nitrate, that middle step, is also highly toxic. And finally, nitrate, while great for plants, is a major public health concern in drinking water. It can cause a serious condition in infants called blue baby syndrome. The other major nutrient we worry about is phosphorus. In most freshwater lakes and streams, phosphorus is what we call the limiting nutrient. Think of it like this. If algae need 100 parts nitrogen and 1 part phosphorus to grow, it doesn't matter if you have 1,000,000 parts of nitrogen. That 1 part of phosphorus is the bottleneck. We specifically focus on orthophosphate because that's the form that's immediately bioavailable to fuel those algae blooms. Okay, let's shift gears. We've talked about what's in the water. Now let's talk about the water's fundamental chemical personality: pH, acidity, and alkalinity. These parameters describe the acid-base balance that controls pretty much every chemical and biological reaction we care about. We'll start with the most famous one, pH. We all learned about it in school, right? But in water treatment, pH is way more than just a number on a scale. It's a master variable. It dictates whether metals will dissolve or precipitate, how well our disinfectants work, and literally whether or not fish can survive. Now, do not make the mistake of confusing alkalinity with simply having a high pH. They are not the same thing. Alkalinity is the water's buffering capacity. It's like a chemical shock absorber. It measures the water's ability to resist a drop in pH if an acid is introduced. This stability is absolutely vital for both biological treatment processes and for protecting aquatic ecosystems. So how do we measure this buffering power? We perform a titration. We take our water sample and slowly add a standard acid, drop by drop, while monitoring the pH. We look for 2 key stopping points, or endpoints. The first one, the P endpoint, is at a pH of about 8.3. The second, the T, or total endpoint, is at pH 4.5. How much acid it takes to get to these points tells us exactly how much alkalinity the water has. And just as you'd expect, acidity is the flip side of alkalinity. It's a measure of the water's ability to neutralize a base. This is most important when we're dealing with things like industrial waste or acid rain. For most natural, unpolluted waters, the main cause of acidity is just dissolved carbon dioxide from the atmosphere. All right, next up are a couple of parameters that have a very direct impact on us as consumers. We're talking about hardness, which can mess with our plumbing and laundry, and disinfection, which is the final critical step in making sure our water is safe to drink. If you've ever wondered why your soap won't lather up or why you get that white, chucky buildup in your kettle or shower head, the answer is hardness. It's caused primarily by dissolved calcium and magnesium ions. We measure the total effect of these ions and report it as one number, expressed as an equivalent amount of calcium carbonate. Now, hardness actually comes in 2 flavors. The first is carbonate hardness, which is linked to the water's alkalinity. We call this temporary hardness because if you boil the water, it precipitates out as that familiar scale. The other type is non-carbonate hardness. It's not affected by boiling, so you guessed it, we call it permanent hardness. After a treatment plant uses chlorine to kill off pathogens, it's crucial that a small amount of it stays in the water. This is the residual chlorine. Think of it as a bodyguard. It travels with the water through the pipes all the way to your house, providing a safety net that protects against any potential recontamination along the way. When you first add chlorine to water, a bunch of it gets used up almost instantly, reacting with all sorts of impurities. This initial consumption is called the chlorine demand. You have to add enough chlorine to satisfy this demand first before you can start building up that protective residual that we need. For our final section, we're going to do a quick rundown of some specific inorganic contaminants. These are things we regulate not necessarily because they're in huge amounts, but because even at very low concentrations, they can cause major aesthetic problems or pose serious risks to our health. Let's start with two very common troublemakers, especially in groundwater: iron and manganese. The good news is they aren't generally a health risk. The bad news is they're a huge nuisance. They're the culprits behind those ugly reddish-brown stains on your sinks and laundry, and they can give water a nasty metallic taste. And here are a few other key players we're always on the lookout for. You've got lead and mercury, which are serious neurotoxins. Then there's sulfate, which can have a laxative effect, and chloride, which makes water taste salty and can be corrosive to pipes. Each one of these tells a different story about where the water has been and what risks it might carry. So as you can see, no single test can tell you the whole story. All these parameters have to work together. The physical tests give us a baseline. Oxygen demand tells us the scale of our organic pollution problem. Nutrients warn us about the risk of algal blooms. pH and alkalinity describe the fundamental chemical stability. And finally, the specific ions alert us to direct issues with usability and health. It's only by looking at this complete picture that we can truly understand and manage our water quality. And that brings us to a final thought-provoking question. Our lab methods are getting ridiculously good. We can now detect contaminants at parts per trillion levels, which is like finding one specific drop of ink in an entire Olympic-sized swimming pool. As our ability to find anything in water gets better and better, how will that change our definition of what's clean or safe? That question is going to shape the entire field of water treatment for decades to come.